over the next couple of minutes, you'll see that it actually has profound implications if one of those is correct or the other. Over the course of my lifetime, there have been a number of landmark contributions to our field. This list could be very long. I don't have time to go through all of them, but I've listed here some of what I think are the fundamental foundational steps that have been made. I entered college in the late 70s, and by the late 70s, the community had more or less come to conclude that the orbital variations are largely responsible for the variations in large-scale climate variability, the glacial interglacial cycles as they've been come to know. But at the same time, in the early 1980s, John Mercer at Ohio State University had begun to make the case that the orbital theory was missing something, and that is that he found that the advance of ice sheets in the southern hemisphere was simultaneous with the advance in the northern hemisphere. And what's more is the retreat of glaciers in the southern hemisphere was simultaneous with those in the northern hemisphere, which would not be consistent with an orbital-only forcing to explain that climate variability. And he went on to suggest at that time that CO2 was a likely synchronizer. And then, of course, shortly thereafter, the ice core community started to develop records of atmospheric CO2, and we've now got a very robust record of atmospheric CO2 that extends back at least 500,000 years. And we're left with now this canonical view of glacial interglacial variability. And you can see here that the term termination is used to describe this transition, this abrupt transition between the cold state and the warm state. But if you also look at this for just a second, you'll also recognize that most of the time the climate has been trying to get cold and has spent a very little portion of its time trying to get warm and staying warm. So in other words, it appears as if, on the face of it anyway, that the climate would prefer to be in a glacial state. Stepping back from that Pleistocene perspective, this is a view of the Cenozoic. This is an oxygen isotope record that reflects the long-term climatic evolution of our planet. And it has a characteristic that it looks very much like the Pleistocene. In fact, if I change the x-axis and use the isotope stages instead, change the y-axis to reflect the Pleistocene 018 variability, it looks very much like an ice age. And there's really nothing necessarily to suggest that the late Pleistocene is anything other than a continuation of this long-term trend. So I pose the following hypothesis, and that is that glaciation is the preferred climate state and has been for much of the Cenozoic. Glaciation is a self-perpetuating state in the absence of something that interrupts it. Glaciations are a result of the erosion of terrain and landscapes that add alkalinity to the ocean and lower atmospheric CO2. And interruptions can occur when the carbon reservoirs are disturbed and add excess carbon to the environment. This is a plot from a paper by Kohler and van der Waal from a couple of years ago, and there's a number of really interesting aspects to this. I don't have time to go through it in detail, but one of the important things is that if you look at the magnitude of the warm phase that has taken place over the course of the last 2.5 million years, the magnitude really hasn't varied much. On the other hand, if you look at the cold phase over the course of these 2.5 million years, it has become progressively colder and colder and larger ice sheets, suggesting, in fact, that the climate has been progressively moving towards a more glaciated climate. Now, they went on, I should say, to point out that there's an inconsistency between the maxima in obliquity and the timing of ice sheet minima. And in the late Pleistocene, those line up only about 52% of the time. So clearly, the orbital forcing is not enough by itself. It requires atmospheric greenhouse gases to bring about the transitions between a warm state and a cold state. So what does control atmospheric CO2? And the prevailing view, shown here in A, is what I call an ocean-only model. And it presumes that the carbon volume in the reactive zone remains constant. And the only thing that changes is that carbon is removed from the atmosphere and put somewhere else, presumably in the deep sea, throughout the course of a glaciation. The alternative to that view is that the carbon sources and sinks are not in balance, and that the sinks have actually been larger than the sources most of the time. Now, each one of these alternatives comes with a set of predictions. The first one, the constant carbon inventory, that calls upon a biological pump and reduced ventilation to explain the drawdown of atmospheric CO2 during a cold phase, predicts that there should be an increased gradient in delta C13 between the surface ocean and the deep sea as atmospheric CO2 is sequestered by the biological pump into the deep ocean. It also requires an increased ventilation age. You have to keep that carbon sequestered in the deep sea away from the atmosphere, and that would predict that there should be a longer residence time of deep waters in the ocean, particularly in the deep Pacific. And then during the ventilation phase in this hypothesis, the gradient should decrease. So we began to look at these and test each one of these predictions. The first one is the surface to deep water gradient. We used the Melitza et al. Database, culled through that database to extract the delta C13 of late Holocene and LGM values for a surface-dwelling planktic form, G. ruber, and a surface-dwelling, bottom-dwelling benthic form, the Cibicidoides. And when we difference the Holocene and LGM for both of these groups, we find that the magnitude is exactly the same. There's no evidence of an increased gradient in the surface to deep water delta C13 gradient as predicted by the ocean-only model. Second of all, the ventilation age. Now, this is a little bit tricky, and I'll just say a couple words about this. If you want to read more about this, you can read the paper I just published in QSR. But basically, the radiocarbon age, ventilation ages are highly, highly contaminated by bioturbation, primarily because most of the data comes from low sediment accumulation rate sites, particularly in the Pacific, which this data is illustrating. If you look at the center plot, you can see that roughly a third of the ventilation ages for the LGM are older than 3,000 years. And if those were right, it would mean the deep Pacific was anaerobic, which it was not. So those values are not correct and should be removed from the database. The second point is that if you remove the most biased values from the low sedimentation rate cores and take only those values with sediment accumulation rates above 5 centimeters a kiloyear, you can see from the bottom plot that the average of the remaining values is basically the same as the modern. There's no evidence of a large increase in the ventilation age of the deep Pacific during the LGM. Finally, there's no change during the deglaciation in the C13 or the C14 gradients between the surface ocean and the deep sea. This is a paper published in 2021. Whereas the ventilation hypothesis predicts that the C14 difference between the surface ocean and the deep sea should decrease, which it did not. Okay, and so the alternative hypothesis, the sources and sinks are not in balance, makes the opposite predictions. And as I've just shown you, each one of those predictions is validated with the available data that we have available to us. So what I would suggest to you for consideration is that these rapid transitions between a cold state and a warm state, what we call the glacial terminations, are better termed interruptions. And that the long cooling that is associated with the buildup of ice sheets in the northern hemisphere is the compensation period between interruptions where excess CO2 is added to the reactive zone. I don't have time to go through in detail all of the examples of places where there is excess carbon available to be released to the ocean atmospheric system. This is just one example from the Western Pacific where John Lupton found that one tiny little single hole in the bottom of the ocean at about 1,600 meters water depth was emitting something like 0.1% of all of the CO2 from mid-ocean ridges in the form of liquid CO2, held in place by a very thin layer of hydrate right at the sediment-water interface that is sensitive to both temperature and/or pressure change. And our community has begun to find that there are radiocarbon anomalies during the last transition between a warm and a cold phase. These radiocarbon anomalies are best explained by the release of geologic carbon. Okay, and I'll leave it there with my summary slide. Thank you very much.
Thank you.